Hello, everybody. Today we have lecture 11. And before we start the lecture, I have to mention that I have found a typo in my previous lecture. Let me check. Yes, it was chapter 4. So last time I said that if we consider Laplacian in L2 defined on the space on the set of infinitely smooth functions with compact support, and then if we consider its closure, then we obtain this domain of definition. There is a typo. The domain of definition should be W22. That is the set of all functions such that they themselves, together with their first and second derivative, partial derivatives, they all live in L2 space. So this is the Sobolev space W22. Okay, and also somewhere before I also yes, so here as well should be 2. Okay, so it was a small mistake, but now let us go to chapter 5. And last time we have formulated the Hahn-Banach theorem for a linear vector space. It is theorem 510. So let X be a vector space over the field of real numbers. Let P be a mapping which is sublinear from X, a mapping from X to R. Let X0 be a subspace of X. And L0 be a linear mapping from the subspace X0 to R, which is dominated by this sublinear mapping P here in X0. Then the statement is that there exists a linear extension L from the whole space X to R. And this linear mapping is an extension of L0, that is this mapping L restricted to X0 coincides with L0, and this extension is such that it is still dominated by the mapping P, that is this inequality holds not only for all X in X0, but also for all X in the bigger space X. So this is the very first statement of the Hahn-Banach theorem. And once again, here we have only linear structure, nothing else. No topology, nothing, just linear algebra, so to say. So let us prove this theorem. And first step in the proof is the following. We consider the situation when dimension of the quotient space X over X0 is 1. That is, the codimension of X0 is 1. So that is, we really need to extend L0 just for one more dimension, so to say. So in this situation, for any X in this space X, there exists a unique element Y, which belongs to X0, such that, and not only a unique Y in X0 and a unique alpha in our field of real numbers, such that X is represented as alpha X0 plus Y in a unique way. So how we define, so let me write down approach for definition of L. So take any real number and so we define the mapping L with index C, and it will be defined like this. So LC evaluated at the point X is defined as follows. This is L0 of Y plus alpha C. That is, I use this representation of X, and then I define L in a way that it is linear. And this means in particular that LC evaluated at x0 is so I have missed to write down that. Okay, so let me finish this first. So I have forgotten the following. So we assume this. This means that there are some elements. So let me write down here. So here, hence there exists small x0, which belongs to x without x0. So we take this x0 and then yes, so hence we can represent any element of x via this sum. So x0 is fixed and alpha and y is, so to say, coordinates of x. Okay, is now clear what has happened?
Yes.
Okay, good. So we have fixed x0. Now we may fix any real number c, and we define a linear mapping by this formula. That is, okay, it is an extension of L0 due to this. And we have fixed x0, then for any real c, we have the corresponding function, linear functional, which is defined like this here, and hence by linearity for all x's, we have this formula. Okay, now we don't need an arbitrary linear functional. We need a functional which is dominated by p. So the idea is let us choose c in a way that this inequality is satisfied. So let us write it down. But first of all, let me write down that here for any c real number LC, of course, it is a mapping from R to R. Sorry, from X to R. And it is linear. And now choose now C such that LC of X is small or equal P of X for any X in the space big X. So this is what we want to do. Of course, first of all, we don't know if it is possible or not. So we have to show that it is possible. So what does mean that LC of X is smaller or equal than P of X for any X? This means that, so I insert the definition of this functional. L0 of Y plus alpha C is smaller or equal than P of alpha x0 plus y. And this inequality holds for any y in x0 and for any alpha real number. So let me somehow save this condition. Let me call it somehow, for example, star, condition star. So we want to show that this condition is satisfied for some c real number. So by our assumptions, this star is satisfied for alpha is equal to 0 and any y in x0. Yeah. Yes, we have this inequality. Oops. we have this inequality. This is the same as what is written here for alpha equal to 0. Okay, so let us now consider other cases. So alpha equal to 0 is okay. Now case alpha bigger than 0. So alpha is bigger than 0, then I can divide this inequality on alpha. And what do we have? We have the following. So L0 of alpha to the power minus 1 y plus c is smaller or equal than p of x0 plus alpha to the power minus 1 y. So I have used the linearity of L0 and sublinearity of P. So P is in particular positive homogeneous. So we can do this. So now I will rewrite it in the following way. This means that my C is smaller or equal than P of x0 plus y tilde. So I will take another color, wait a minute. So this is my y tilde. So P of x0 plus y tilde minus L0 of y tilde, and this holds for any y tilde in x0. And this means, so this is equivalent to the statement that C is smaller or equal than infimum over all y tilde in x0 of this expression P of x0 plus plus y tilde minus L0 of y tilde. And I want to save this inequality. And let me call it inequality A. So we have not shown that this inequality is true for some C's, but this is what we want to show, that we want to find C such that this inequality holds. But so first of all, I collect all our wishes. So this is wish number A. We want to find such C that A is satisfied. But now we have to consider also the case alpha smaller than 0. Before we consider it, let me copy it in the next slide. But probably I have switched to the next slide too early. So this is the slide which we were working with. Have you finished? May I go further or not? Okay, so let us continue on the next slide. So we have this inequality. So we want to find C such that this inequality holds. So for case alpha equal bigger than 0, this inequality is equivalent to this inequality. Now case alpha smaller than 0. Again, we consider this inequality. And we of course can divide with alpha again, but we should take into account the sign of alpha. So this star is equivalent to the following. Minus C is smaller or equal than 1 over absolute value of alpha. And here P of alpha x0 plus y minus L0 of y. So I have just divided on alpha, taking into account the sign of alpha, nothing else so far. But now I rewrite this right-hand side. This is P of y over absolute value of alpha minus x0 minus L0 of y over absolute value of alpha. And this is again my, I don't know, y tilde, which belongs to x0. Hence, all this is equivalent to the following statement that C is bigger or equal than supremum over all y tilde in x0. And here we have L0 of y tilde minus P of y tilde minus x0. And I save this inequality. This is inequality B. So I can say that, so my star is equivalent to A and B, probably. Both A and B should be satisfied. So the set of all real numbers C such that A and B are satisfied is not empty. This is the statement. Indeed. So we show this statement. And as soon as we show this statement, we show that there exists at least one real number C, such that this guy, this concrete guy, is the extension which we want. Okay, so we show that the set is not empty, indeed. What does mean that A and B are satisfied? This means that, okay, so this is B, so C is bigger or equal than this supremum, and this is A, C is smaller or equal than this infimum. So in order to have a C such that both inequalities are satisfied, we need to show that this infimum is not smaller than this supremum. So this is what I'm going to write down. So this is satisfied if L0 of y minus P of y minus x0 is smaller or equal P of x0 plus y tilde minus L0 of y tilde for any y and y tilde in x0. So instead of infimum and supremum, I take just arbitrary two elements of x0. So in one side we have this y, in another side we have this y tilde, and this inequality should be satisfied. So infimum should be not smaller than supremum over vice. Okay, and now I rewrite this in last inequalities in the following way. So this means that now I use linearity of L0. This means that L0 of y plus y tilde is smaller or equal than P of x0 plus y tilde plus P of y minus x0. And this holds for any y and y tilde in x0. And I call this inequality, inequality C. So A and B are satisfied, then if and only if C is satisfied. So this is the thing which we want to show. Yes. So let us show it. By our assumptions, for any y and y tilde in x0, we have the following. So recall that y and y tilde, they are elements of x0. x0 is a subspace of x it is a vector space itself. Hence, this sum is again an element of x0, and hence we may use this inequality for this element. So L0 of y plus y tilde is smaller or equal than P of y plus y tilde. But this is nothing else but P of y minus x0 plus x0 plus y tilde. And now I use sublinearity of P. My P is sublinear. That's why this is smaller or equal than P of y minus x0 plus P of x plus y tilde, x0 plus y tilde. And hence we have obtained exactly what we wanted here. Hence C is okay, satisfied. Okay, so using sublinearity of P and this domination, we have shown that this inequality holds, that is, this inequality holds, that is, A and B are true, that is, this inequality holds. And this means that there exists C such that such linear functional is an extension such that we want. Nobody said that this is a unique extension, but it exists. Okay, other questions so far?
No, it's very clear.
Okay. Now it was only first step. It was the step when we have this nice dimension of x0. That is, we really needed to extend our L0 only, so to say, for one dimension more. Now now we have to show the general case. So step 2, general case. General case. So now my x0 may have any codimension. And for proving this case, we need We need the lemma of Thorn. Thorn lemma. And I have it here. Okay, I have copied some, what is it? It's strange, I have copied it here, but it also appeared here. No, this is something new in my experience. Okay, I cannot kill it. At least I don't know how to kill it right now, but we will survive with it. So first definition concerning the Thorn's lemma. So let M be a set. A partial order on a set M is a relation with the properties. So if so for any each element of this set, x is smaller or equal to x. This smaller equal, this is not smaller equal, this is this relation. So x is related to itself. Let me say smaller or equal, otherwise it's hard to describe. So for each element x in M, x is ordered with itself. If x is in this relation to y and y is in this relation to z, this implies that x is in this relation to z, and this holds for any 3 points of M. So reflexivity and transitivity, and also if x is in this relation to y and y is in this relation to x, this means that x is equal to y, so antisymmetry. So the lemma of Thorn states the following. If we have a set which is partially ordered using this relation, and M is a non-empty set, and another assumption that every totally ordered subset has an upper bound. So totally ordered subset is a subset of M such that for any two elements of this subset, they are ordered. So either they are in this relation or they are in this relation. So they are comparable with each other. Partial order means that we have a relation, and so if something holds, then this holds. But it is not required that all elements are comparable with each other, are related, are in the relation to each other. So totally ordered subset, any subset whose elements are ordered via this partial order. So the assumption is that for any totally ordered subset of this set, there exists an upper bound. That is an element in this set such that it is such that this element is an upper bound for all elements of this set. So of course I don't like how it looks like, and I don't know what to do with it. No? Strange. Okay, I hope that you can read what is written. Okay, so the statement of the lemma of Thorn is that in this case, the set M, which is only partially ordered, not totally ordered, has a maximal element. That is an element of this set, such that it is an upper bound for all elements of M. That is, if we have some element of M which is, so to say, bigger or equal than M, then X is nothing else but M. So remark that a maximal element does not need to be unique. It starts writing. No, it does not want. Strange. Okay, I hope that the lemma of Thorn is something known for you, and we have already discussed it in some previous lectures. So this is the object which we are going to use, and now how we are going to use it. So consider the set M Let me write down it like this. This is the set whose elements are couples V and LV. What are these objects? So V is a vector, is a subspace or vector subspace of X such that X0 is a subset of V, so extension of X0 to some subset, a subspace, and LV is a linear functional, so it's a mapping from V to R, linear, such that LV restricted to X0 coincides with our L0. And LV is dominated by P. So what does it mean? This means that my M is the set of all possible admissible extensions of L0. Admissible means that they are they remain to be dominated by this mapping P. So we may create a partial order on M. So we say that this couple V1 LV1 is smaller or equal than a couple V2 LV2 if and only if V1 is a subspace of V2 and L V2 restricted to V1 coincides with L of V1. That is, two couples are ordered if one couple is just an extension of the previous couple. Okay, so we have to check that. So we have a set, we have a partial order. We have to check next assumption of the lemma of Zorn that each totally ordered subset of M has an upper bound. So what do we have? So first of all, what we have that this M is not an empty set. It was one of the requirements of the lemma of Zorn. And this is here. Non-empty set. M is partially ordered non-empty set. So M is not empty since the original X0 and L0, this is an element of M. So what we have introduced above, partial order. So this is really, it is a partial order. I hope it is more or less obvious that the conditions which are given here are satisfied. And now we have to check that each totally ordered subset of M has an upper bound. So let us show it here. I guess I have to go to the next slide because here we have not that much place. Or probably I will just write down here. Okay, so what do we have more? So we have a family V lambda L V lambda. Lambda is parameterized by some parameter set big lambda. So let this family be a totally ordered subset of the set M. Then let us define V as follows. This is just a union of all lambdas of these vector subspaces V lambdas. This guy is a vector subspace of X since, so I will write down here on the left hand side, if X and Y are two elements of V, then there exist two lambdas, lambda 1 and lambda 2, such that, for example, X belongs to V lambda 1, Y belongs to V lambda 2, but since we are living in this totally ordered subset, we have either V1 is a subspace of V2 or V2 is a subspace of V1. Hence, X and Y live, so to say, in the same space, so that so the bigger one. So for example, if we are in this situation, we may consider X and Y as elements of V2, but this is a vector space, hence we may consider linear combination of these two vectors of this bigger space, and this linear combination lives in this bigger space, and hence also here. So we obtain that V is a vector space. So it's a correct object. Agree?
Yes.
Okay. Now I have to go to the next slide. This what I really wanted to avoid, but okay. I hope that you have your own notes, so you keep on seeing what was written before. Okay, so this is my V. Now I want to decide to define LV. So I define LV of X such that it is equal to L V lambda of X for X belonging to V lambda. Then LV is well defined. Since if so let me say, so if we have so let me write down like this: LV1 of X1 is equal to LV2 of X2 if X1 is equal to X2. So this guy belongs to V1, this guy belongs to V2, and hence this element belongs to the smallest of these two vector spaces. So I may write down like this. So all our vector spaces are totally ordered in this family V lambda, and hence such a definition does not contradict to the fact that we may consider this X as an element of different V lambdas. Okay? So conclusion, hence this V and LV is an upper bound for this family V lambda L V lambda lambda in big lambda. Hence, this assumption of the lemma of Zorn is also satisfied, that each totally ordered subset of M has an upper bound. Therefore, by Zorn's lemma, there exists a maximal element x tilde L tilde in M. Moreover, we have that this x tilde, which is a vector subspace of X, is just a whole space. Since otherwise, one can, as in step 1, extend L tilde from X tilde to a vector subspace of one more dimension. So this is, so if X tilde is not a whole space, there exists an element which belongs to X but not to X tilde, and hence I can consider this vector space. So I just add the linear span of X0 to this X tilde. So I have a vector space such that in this vector space, codimension of X tilde is 1, and hence using step 1, I can extend L tilde from this subspace of this space onto the whole space. And this, what will give us this extension? The new part, so the new couple, so a bigger space, and then L extended to this bigger space. Is again an element of M and is bigger or equal than the previous couple. And this is just a contradiction with X tilde L tilde being a maximal element. Hence, L tilde is an extension of L0 with desired properties. And we have proved the Hahn-Banach theorem. So how to extend for one more dimension? It is shown by hands. Then one uses the lemma of Zorn that, roughly speaking, starting, so we can extend for, so iteratively for one more dimension and then for one more dimension and then for one more dimension. So we may have many different extensions to somewhere. And we have shown that the set of all possible extensions, this set satisfies all assumptions of the lemma of Zorn. So on the base of this lemma of Zorn, we find a maximal element, which does not need to be unique. So do you have any questions or comments concerning the proof of this theorem?
No.
Okay, then exercise. Oh, no, not yet. Not yet. Okay, then I'm very surprised. So now it will oh God. So this is something new. I don't know how to kill this stuff. It does not want to be erased. It does not want to be deleted. No. Very funny. Probably I try to kill it here.
Yeah, you have to kill the zero patient.
What I have to kill?
The patient zero, like with zombies or something.
I don't
You
understand.
have to kill the first infected person, and then you stop the zombie virus.
Yes,
something.
but there is no such an option, you see. Oh God. Okay, so this is something strange with the program. So I have never had anything like this before. No. No. Okay, let us survive somehow with this. Okay, so we have proved theorem 510. Now, theorem in the case of complex numbers. We are not going to prove it. I just explain what is the modification. So if we have complex numbers as the field, then let X be a vector space over C over complex numbers, X be a subspace, P a sublinear mapping, L0 a linear mapping from some subspace. And then the domination is given by, so the real part of this L0 is dominated by a sublinear mapping. Then there exists an extension such that the real part of this extension remains to be dominated by P. Okay, so the proof is totally similar. We need just a small modification. Modification is given by the lemma below. Okay, I will never use copy paste anymore. Okay, so the lemma. So we have a vector space over C. So with this symbol, only here, only in this proof, with this symbol, so not a snowflake, but the star and index C. So this is the set of all C linear functionals on X over C. So X is a vector space over C, and I consider C linear functionals, that is functionals which map X to C and satisfy this linearity stuff. Where my coefficients alpha and beta, they belong to C. So this is this C. This is in one hand. And then let us consider this set. This is the set of all R linear functionals on X over R. That is they map, so how to say, okay, they map L from X to R, and this holds for alpha and beta from R, not for all complex constants. And even this is not quite nice. This means that so in the second case, this means that we consider X as a as what? So let me not go deeper. So this set is a set of functionals which map x into R, and this is satisfied for real coefficients alpha and beta. Okay, and let us consider this mapping A, which acts as follows. So linear functional from this space is mapped to its real part. So the statement is that this mapping is linear, R-linear, bijective, and this holds. That is, what does it mean? This means that if we have a real part of a linear functional, we may recover the whole functional using this formula. And this recovering is a linear procedure, bijective, and this is how it works. So this is one statement. Another statement is that, so if P is a semi-norm, L is a linear functional in this sense, so C linear functional, and we have, so if P is not just subadditive, as it was in the Hahn-Banach theorem, sublinear. If we have something more, if P is a semi-norm, then this inequality is equivalent to this inequality. So as I said, once again, let me repeat. So Hahn-Banach in the complex case, we may dominate the real part of the functional L. So if P is not only sublinear but a semi-norm, then this domination of real part is the same as is equivalent to the domination of absolute value. So in this special case, we may rewrite the Hahn-Banach theorem for complex case with this inequality. And if, moreover, P is not only semi-norm but a norm, so even better situation is a special case. So if X is a norm space, that is, we use SP the norm in the Hahn-Banach theorem, then we may the norm of L in this space is a space of bounded linear or continuous linear functionals, C functionals. It is the same as the norm of real part of L in the space of all continuous real valued R linear functionals on X. Okay, so this is just the modifications which one has to make in order to consider the case of complex numbers, but everything is purely technical, so we are not going to go to details and prove all the technicalities. Okay, so now the most interesting case for us, the Hahn-Banach theorem for norm space. That is, it is a special case of all what we have seen previously. But now X is not just a vector space, but a vector space endowed with the norm. So we have a topology, perfect. And this norm we use as this sublinear P, which was used before for domination. So theorem, so let X be a norm space over real or complex numbers. Let X0 be a subspace, not necessarily closed. So let L0 be a continuous, it's important, linear functional, that is, it belongs to this space. So here we have a snowflake. Then there exists a continuous linear functional on the whole space, that is the element of this space, topological dual to X, such that L restricted to X0 is L0 and the norms are preserved. So the norm of L as an element of topological dual to X is the same as the norm of, here is the typo, so the same as the norm of L0 in the space of in the space which is topological dual to X0. Okay, so we have to show this as well. Okay. Case 1. K is real numbers. Again, this stuff is obtained in the same way as here, using this result. So case 1, K is equal to R. Set. So we consider this sublinear mapping, which is defined as follows. It is the norm of L0 in this space of continuous linear functionals from x0 to R, that is topological dual to x0 times norm of x. So this is just a constant. So for any x, in x, we define the mapping Px as follows. So this is a norm of x times a constant. Then this P is a mapping from x to R. Actually to this interval, and this mapping is sublinear. And hence, there exists mapping L from x to R, which is linear, which is the extension of L0, and which satisfies that L of x is smaller or equal than norm of L0 times norm of x in x. This is my P of x for any x in x by the Hahn-Banach theorem, which we already proved. It was Theorem 510. What was 511, by the way? Oh, this remark. Okay. Okay. Furthermore, for any x in x, we have the following. Minus L of x, we use the linearity, this is L of minus x, is smaller or equal than P of minus x by this and this is nothing else but this norm of L0 in this space times norm of minus x, which is the same as norm of x. Hence, in total, so to say, we have that absolute value of L of x is smaller or equal than norm of L0 times norm of x for any x in x. And what does it mean? So first of all, let us start once again, look through the proof what we have done. So what do we have? We have a continuous linear functional on a subspace. Now we define this P. It is sublinear, defined on the whole space. And of course, from this definition, we see that L0 is dominated by P. So we may apply the theorem of Hahn-Banach, theorem 510, for vector spaces, which guarantees that there exists an extension L, an extension of L0, which is again dominated by P, point. Now we have to show that this L is not only a linear functional, but it is a continuous linear functional. That is, it belongs to these spaces. And we have to show that this identity for norms is satisfied. So this is what we are going to do, this is what we are doing now. So this is our consideration. So we have obtained this inequality. From this inequality, we see that that L is a bounded or continuous, equivalently continuous linear functional. And we also see that the norm of this functional L in the space of continuous linear functionals on X is smaller or equal than the norm of L0 in its space. You know what should be there. Okay, so this is what we have shown. Agree?
Yes.
Yes. So now we need equality, not inequality. So let us guarantee that it is. So on the other hand, so norm of L in this space, it is supremum over all, what's going on? Over all x's with norm equal to 1. We may use this form of absolute value of L of x. This is bigger or equal than supremum over a smaller set. So let me write down in this way. Oops. It doesn't want. Supremum. Here we have over all x's in x such that norm of x, okay, equal to 1, for example, or smaller or equal to 1. This is not that important. Now I consider the supreme over a smaller set. Supreme of the same things, but supreme over a smaller set. The smaller set is x in x0 with the same condition on the norm. And this is the norm of L0 in its space. Hence, that's it. So we have, on one hand, we have this. On the other hand, we have this. So we have shown that this identity holds, and this we have also shown, and the existence of an extension is shown by the Hahn-Banach theorem for vector spaces. Okay. Agree? Everything is fine?
Yeah, I think it's clear.
Okay, then case 2 car is equal to C by this lemma star, which was here. Okay. That's it. So this is the most interesting case for us. We have a norm space, and no matter how big this space is, and no matter how small x0 in X is, if we have a continuous linear functional on x0, using the Hahn-Banach theorem, we may extend this functional to a continuous linear functional on the whole space. this nice result can be used, for example, to show that any Banach space or any norm space X possesses a dual space, topological dual, which contains not only trivial linear functional. So exercise, which is very simple, and it is for right now. Exercise show that for any Banach space X, or actually norm space, not necessarily Banach, there exists a non-trivial continuous linear functional on X. So we have all the tools. So I suggest you to think about how to show it. No technicality, it's just the approach. Non-trivial means not like this. Are there any ideas?
We can take some non-zero vector
Yes.
and take the orthogonal complement
No,
to
there
this.
is no orthogonal complement in the norm space.
Oh yeah, I see. Mhm.
Yes, but still, we may take a vector x0 then.
Yes, so we take our linear functional to be some alpha on this vector, have some value on this vector.
Mm-hmm. And then we can...
And then we extend this. So yeah, we take this vector, we define our functional on this subspace, which is just a span of this vector.
Yes, so one dimension.
And then we...
Yes.
Mm-hmm. And then we extend it using the Hahn-Banach theorem.
Yes, exactly.
Something like this.
Yes. So for one-dimensional vector spaces, we know how linear functionals look like. So actually, for any finite dimensional norm space, all linear functionals are continuous. So we take any finite dimensional vector space, a subspace of this norm space, define any linear functional in an easy way. For example, one-dimensional subspace, everything is perfect. We have discussed it, I guess, last time, but oh, it will be very far away. Okay, yes. So in finite dimensional subspace, we know how to define linear functional. They will be automatically continuous, and then we extend them by Hahn-Banach theorem. Okay, now we get even more. So corollary 13. So let X be a norm space, X0, some element, non-zero element. Then there exists a continuous linear functional such that L of X0 takes this particular value, and the norm of this linear functional is just 1. Furthermore, this space not only contains some non-trivial elements, but this space is big enough, namely it separates the points of X. That is, for any two different points in X, there exists a linear functional in this space, which distinguishes these 2 points. That is, the values of these functionals at these 2 points are different. Okay, so this is what we have to show. So somehow I was quite slow today in the morning. So okay, let us. Okay, let us somehow survive with this. Let me take another color to distinguish the proof. So consider, so exactly as you suggested. So consider X0, which is just a one-dimensional space, oops, k times x0, this is just nothing else but the linear span of x0. So one-dimensional subspace of x. So define L0 in the following way. So L0 of alpha x0 is defined as follows. This is alpha times norm of x0 for any alpha in K. Then L0 is linear and continuous, and norm of L0 in X is just 1. And L0 evaluated at x0 is just the norm of x0. So x0 is a Hamilton basis in this space. And then, so this is the linearity, so to say. And this is my C, the value of my functional at the point x0. And this is the linearity then. Okay, and one-dimensional space, so any linear functional is continuous. Okay. So we have this. So by it was theorem 512 by Hahn-Banach. Theorem 512 extend L0 to L in X star to a linear continuous function on the whole space. That's it. So we have shown this statement. Now let us show this statement, second statement. This is also important. So let x1 and x2 are 2 points in X. So consider x0, which is just the difference of them. This is not a zero element, so it satisfies this assumption. Then we may construct the corresponding L. So there exists L, a linear continuous mapping, such that L of x1 minus x2 is just norm of this element, x1 minus x2. And this is not zero because x1 minus x2 is not zero. Wow, what's going on? The norm of L in X star is equal to 1. Okay, this is even not that important now. We have this, and that's it. Hence, we have that L of x1 is not equal to L of x2. Okay, so the proof was very simple. But the conclusion is very important. So for any norm space, its topological dual is a sufficiently big space which separates the points, or distinguishes the points of X. So may I go further to the next slide?
Please.
Yes. So remark, so corollary 513 states that X star is rich enough to distinguish elements from X. That is, 2 points are actually the same point if and only if we have this identity for all linear functionals from topological dual. This viewpoint is the basic idea for weak formulations in the theory of partial differential equations. Namely, for each element X in our norm space, we may consider this family. So this is the family of all values of all linear continuous functionals on X. all their values at this point x. So this family may be considered as generalized coordinates of this point x. And due to this fact, so different points of x have different generalized coordinates. So please remember this idea. We will discuss it later on, not right now, but this is somehow important. Okay, so let us go further and consider further corollaries of the Hahn-Banach theorem. So one more corollary in a sense. One can show in a similar way as here that for each infinite-dimensional normed space X and for each natural number n, there exist n vectors in X and n linear continuous functionals on X, such that we have these identities. And this means, in particular, that this topological dual space is also infinite dimensional. So this is an exercise. You may use Hamil basis in X and this type of corollary to construct the desired linear functions. Okay. Each time when I see it, I'm very upset. Okay. So next corollary, but before we discuss this corollary, we need some definitions. So I recall some definitions which probably you know already. So let x0 and x1 be subspaces of a topological vector space. So we have a vector linear structure and we have a topology. First definition. So we may consider the object which is called an algebraic direct sum of these two subspaces. So one may understand, so these are the elements of this algebraic direct sum, where x0 and x1 are elements of these spaces. So this object is an algebraic direct sum if and only if the addition, so this operation, is an isomorphism of vector spaces. That is, A is a linear bijection. Yeah, so A has an inverse mapping, and so A is linear and A is one-to-one in bijection. And it is claimed that for any subspace x0 of a vector space X, there always exists its complement, algebraic complement, that is a subspace x1, such that one may represent the whole space X as an algebraic direct sum of x0 and x1. I hope this is a kind of obvious and clear statement. Okay?
Okay.
Now, topological direct sum. So this object is called a topological direct sum under the same assumptions. If and only if the same procedure, addition, so this operation is an isomorphism of topological vector spaces, not only vector spaces, but topological vector spaces. That is, A is not only a linear bijection, but A and its inverse both are continuous mappings. So not only with linear structure everything is fine, but also with topology everything is fine. This means that to construct a topological direct sum is a more complicated procedure. It requires more assumptions. So what is written here? So this P0 is a projection of this object, so algebraic projection of this object to the first coordinate, and P1 is a projection, algebraic projection of this object to the second coordinate. So these mappings, they are defined pure algebraically, but so this mapping A should be bijection, and A and its inverse, they should be continuous with respect to a given topology. In this situation, not all subspaces of a norm space are topologically complemented. So it's not possible sometimes to create, okay, one can create an algebraic complement, but the topological structure will be violated. So it will be not a topological direct sum or topological complement. So further, let X be a norm, let me write down. Let X be a norm space, X0 and X1 subspaces of X. And we know that X is a topological direct sum of X0 and X1. Then one can show that both subspaces are closed subspaces. One more statement that every closed subspace of a Hilbert space is topologically complemented. In order to prove it, one can use the result which we have already proved, that in any Hilbert space there exists an orthonormal basis. And this so then there is an orthogonal complement, and it is even without orthonormal basis, we have orthogonal complement, and this makes everything. But this happens in the Hilbert space where we have orthogonality. In Banach spaces, the situation is versa, and actually every Banach space that is not a Hilbert space possesses a closed subspace that is not topologically complemented. That is, of course, algebraic complement exists, but this algebraic direct sum is not a topological direct sum. So there are problems on the level of topologies. Okay, remark. So a corresponding version of the Hahn-Banach extension theorem for spaces is not true for arbitrary linear operators. Yeah, so linear functionals is a special case of linear operators. So linear operators are just linear mappings from norm space to a norm space, and linear functionals are a special case when my y is just a field of numbers. So we have a very nice Hahn-Banach theorem for this special case of linear functionals, but a similar statement about linear operators is not true, and this is a counterexample. And this counterexample is exactly related to what we have discussed right now. So not all closed subspaces are topologically complemented. So a counterexample. So let X be a Banach space of all bounded sequences. X0 is a subspace of X. It is a space of all sequences which converge to 0, and this is also my Y. We have already specified somewhere before that this is a closed subspace of L infinity, so they both are Banach spaces with supremum norm. Okay, so let us consider a linear mapping, a linear operator from X0 to Y, which is just an identity mapping. Yeah, from C0 to C0, identity mapping. It is a linear and continuous operator, obviously. But this operator L0 does not have an extension to a continuous mapping from X to Y, because if there would be such an extension, what would this mean if there would be a continuous mapping L? So this mapping L acts from X to Y, and it is a kind of projection from X from this space to this space projection. So if there is this continuous mapping, which acts like identity on this subspace, then this mapping would be continuous. We have shown that there exists A such that this guy is continuous. But then this P1 can be shown also continuous, and then we obtain a topological direct sum. That is, we represent L infinity as C0 topological direct sum with something. But this is a known result that this subspace of L infinity is not topologically complemented. So it is not possible. So this statement can be found in the book of Werner, Functional Analysis, but this is a book on German. But it's a good book, and now we have a lot of tools which allow to translate texts. So one can read any book and on any language. Okay. So summary, what I wanted to say. So a corresponding version of the Hahn-Banach extension theorem is not true for linear operators. This is one important information. And another important information is not all subspaces of a norm space are topologically complemented. But if they are topologically complemented, then the topological complement should be closed. Okay, let me write down like this. Okay. Corollary. So let X be a norm space, X0 a subspace of finite dimension. So all finite dimensional subspaces of a norm spaces of a norm space, they are closed. This we have discussed already. So then X is topologically complemented. That is, there exists a closed subspace X1 such that X is the topological direct sum of X1 and X0. That is, X is an algebraic sum, direct sum, and the natural algebraic projections are continuous. So we still have a little bit of time, so let us prove it. First of all, I have to find the proof in my notes. Okay, hopefully this is the proof. Okay, so let x1, etc., xn be a Hamil basis of x0. X0 is finite dimensional, so our Hamil basis is finite. By a remark, what was this remark? So I have to find the number. This remark, 15. By remark 515, there exists functionals L1, Ln, which are continuous linear functionals with the property that Lixj is equal to delta ij. So let x1 be defined as follows. It's an intersection, so finite intersection of kernels of these linear functionals. So let us define P0 as follows. So P0 of X is the sum I from 1 till n, Li of X, Xi, and P1 is defined as follows. P1 of X, this is just X minus P0 of X. Then P0 and P1 are linear, obviously, because this is just a linear combination of linear functionals Li with some coefficients. Okay, so P0 is linear, identity operator is linear. So this operator is also linear. Moreover, for any j from 1 till n, P0 of xj is equal to Lj of xj. This is just xj. That is P0 restricted to x0 is equal to identity, and P0 restricted to x1 is equal to 0, because we have this linear. P0 is a linear combination of Li, and x is the intersection of kernels of all these functionals Li. So this P0 is an algebraic projection onto x0, and hence P1 is the corresponding algebraic projection onto x1. That is x is equal to x0 plus x1 algebraically. Algebraic direct sum. Now continuity. Continuity of P0 and P1 is clear from definition, not only linearity but also continuity, because these functionals are continuous. So linear combination, finite linear combination of continuous mappings is a continuous mapping. Identity operator is a continuous mapping. So this is again a continuous mapping. So these guys are continuous. Hence, so this x is equal to x0 plus x1 topological direct sum. Okay, that's it, and we have not that much time. I mean, we don't have time at all, but I actually expected that we do more today. But what we have succeeded so far. We know that in norm spaces, not all subspaces are topologically complemented, but at least finite dimensional subspaces, they are topologically complemented. Okay, so this is it. And we still have some things which we have not yet discussed, namely a little amount of further corollaries of this Hahn-Banach theorem, and then an interpretation of a Hahn-Banach theorem, so, a geometric interpretation of the Hahn-Banach theorem, which is the Hahn-Banach theorem which we have discussed today, it is like a Hahn-Banach theorem about a continuous extension. And there is also the so-called Hahn-Banach separation theorem about the possibility to separate disjoint convex sets using linear functionals. And this is an important result, for example, for calculus of variation. So everything what is so there is the so-called convex optimization. This is a field which is extremely important, not only for PDEs, but also for data science. And so convex optimization is a very rich theory, and So the idea is that if we optimize nice functionals over convex sets, then we so it is a well-posed problem, so to say. It's doable. And so actually everything is not everything, but one of the important cornerstones of the theorem is exactly this Hahn-Banach, which allows to obtain this well-posedness of minimization or optimization problems of the convex sets. Okay, so this will be discussed next time. Sorry, it seems I was quite slow today, but I hope it was better than just to be fast but totally ununderstandable. So, do you have any questions or comments so far?
I want to add a comment.
Yes?
Okay, I want to thank you for distinguish the two isomorphisms. Before today, I know that there exist at least two different isomorphisms, but I don't know why. And today I understand it's the space we discussed when topological space we need the isomorphism to be bilinear continuous and also the inverse should be continuous.
Well, I'm sorry. It seems that the connection either by you or by me is not quite good because I actually could not understand what you have said.
I just want to thank you for distinguishing the two different isomorphisms, the definition. I mean,
You mean isomorphism of vector spaces and topological vector spaces?
yeah, yeah, yeah.
Yeah, so
The
it's an important smallness, so to say. It's an important object, yeah. Okay, then I stop the recording.